Now, here we go. Here we go. Let's take a look at a couple of these volcanoes. Some of these volcanoes are visible from space. So, for example, if we look right here, these three little spots, those are volcanoes. This is a volcano right here. There's a couple more volcanoes over here. And here's the next question. If we can see some of the volcanoes from space, what does that tell us about those volcanoes? Yes, they must be very, very, very big, okay? So the volcanoes on Mars tend to be very, very large. In fact, the Mars, even though it's a relatively small planet, the volcanoes, it has actually the largest volcanoes in the entire solar system. And the very, very biggest volcano in our entire solar system is this one right here called Olympus Mons, at least if we're going by height, okay? So the Olympus Mons right here is the biggest volcano in the solar system. And I know you probably can't read that very well, so I'm going to bring it up on another slide. So up there, I have Olympus Mons. That's the biggest volcano, not just on Mars, but also in the entire solar system, okay? And it's named after Mount Olympus from Greek mythology, okay? Now, here we go. How big is it? Well, check out the scale down here. This right here is 50 kilometers. And I know you guys aren't used to dealing with with kilometers if you grew up in the United States, but that's very big. So this picture of Olympus Mons here is actually about the same size as the state of Arizona, okay? So if we were to put this volcano onto the Earth, it would be as wide as the state of Volcano. This volcano would be as wide as the state of Arizona, okay? So it is very, very large. In terms of height, this volcano is a little over 2.5 times the height of Mount Everest, okay? So it's 2.5 times bigger. So you could stack up two Mount Everests on top of each other, and it still would not be as tall as this volcano, all right? And one more thing I should say to give you guys an idea of how big this particular volcano is see this hole in the top here where the lava comes out? That hole is bigger than the state of Rhode Island, okay? So if you needed to sacrifice some people to this volcano when it was active, you could just take the entire state of Rhode Island and throw it into the volcano all at one time, and it would fit into that hole of lava. It would actually be hard for you if you were standing on one side of the hole at the top of the volcano. It would be hard for you to see the other side of the hole at the top of that volcano. So that's very, very, very big. All right. Now, so why are these volcanoes so big on Mars? Let's figure that out. Now, to do that, I'm going to bring up a picture. I'm going to bring up my document cam so I can draw a picture. Here we go. Boom, boom, boom. So just to make sure, let's see. Okay, that's running. All right. So here we go. Let's imagine thinking back to when Mars was fully active. So like think back in the past when Mars used to be active. So it had a crust just like us. Well, it still has a crust. Like this. There we go. Well, you know what? Let me get a better pen. Let's use this red one. Okay, here we go. So imagine that that's the crust of Mars. Bring this down. There we go. So that's the crust of Mars. Underneath it, back when it was active, it had an asthenosphere. So this is the crust, and this is the asthenosphere. And down here we have the rest of the mantle. So crust, asthenosphere, rest of the mantle. Okay, now here we go. There are places at the bottom of the asthenosphere, or rather at the top of the rest of the mantle, which are pretty hot. And what do we call these hot spots? We call them hot spots. Okay, so these spots in the upper part of the rest of the mantle that are hot are called hot spots. Now, if that spot is hot, what it's going to do is it's going to heat up this part of the asthenosphere. So the magma right here above the hot spot will be hotter than everything around it. And if it's hotter than everything around it, what is it going to want to do? What is that hot magma going to be going to do if it's hotter than all of the material around it? Yes, that's correct. It's going to rise. It's going to rise because of convection, right? And what that's going to do is it's going to cause hotter material to go up here, and it will slowly melt its way through the crust. It'll open up a hole if enough hot material rises there, and that hot material will come out, so that lava will come out. And what's the temperature like on the surface of Mars compared to inside? It's colder, right? And if it's colder, what's going to happen to that hot lava when it comes out of the hole? If it cools off enough. Right. It'll cool down, and it will turn into solid rock. So what happens is around this opening above the hot spot, you're going to get a pile of rock around the edges. Where lava comes out, what is that? What did we just make on the surface above that hot spot? Yes, that's a volcano. That's a volcano. Does that make sense? So what would make this volcano grow? So we know Mars's volcanoes got really, really, really big before they turned off. So what makes the volcano grow? Yeah, so I see somebody said a bigger hotspot. A bigger hotspot would make a bigger volcano, but you don't necessarily need a bigger hotspot. You just need that hotspot to stay hot. Because as long as that hotspot stays hot, material will continue to rise out of that volcano, and every time it erupts, that eruption will leave more solid rock around the surface, on top of the volcano. And that means as long as that volcano keeps erupting and erupting and erupting, that volcano is going to keep getting bigger and bigger and bigger. So the reason that Mars's volcanoes got so big is that they continued to erupt for a very, very, very long time. Okay? Now, here's what we have to figure out. Earth still has active volcanoes. We've been active for a longer time. So why is it that our volcanoes don't get as big as Mars's volcanoes? So here we go. Let's check this out. So what's different on Earth? So we still have a crust. We have an asthenosphere. And we have the rest of the mantle, just like Mars used to have when it was still active. And we still have hotspots. We have hotspots just like Mars used to. And wherever those hotspots cause material to rise, we will get volcanoes on the surface. Okay? But somebody mentioned the answer to what's going on here. Why do our volcanoes not continue to grow? What does our crust do that Mars's crust did not do? What does our crust do that Mars's crust did not do? Yeah, it shifts and moves because of plate tectonics. So what happens is the only part that's moving here because of plate tectonics is the crust. The hotspot doesn't move. So if the crust of Earth were to move that way, the volcano would get off of the hotspot. And if that volcano gets off of the hotspot, what happens to that volcano? If it's no longer on the source of rising material, what happens to the volcano when it moves away from the hotspot? Yeah, it stops erupting and it dies, so it stops growing. But that hotspot's still there. So what happens is the hotspot just makes another volcano where the old volcano used to be. But then eventually the crust will shift again, and so what will happen is we'll have 2 dead volcanoes in a row and a new active volcano showing up. So instead of having one big volcano, what do we get on Earth? Yeah, we get a long chain of dead volcanoes, okay? We get a lot of small volcanoes. What's a good example of that on Earth? There's a pretty good example of a long chain of volcanoes on Earth that we can look to. It's part of the United States. Hawaii. Someone mentioned the Ring of Fire. That's a little bit different because that's volcanoes that pop up on the edge of plate boundaries, at fault lines, essentially. But Hawaii is in the very middle of a plate. So it must have come from a hot spot, okay? And so the Hawaiian Islands are just a chain of volcanoes. They basically look like this. That's Hawaii. Are all of the volcanoes in Hawaii active? The answer is no. Does anybody know which Hawaiian islands are active? Yeah, it's these big ones over here. So these ones over here, the really big ones, are right on top of the hotspot. If we could see underneath them, underneath the crust, we could eventually look down far enough to see this hotspot. And the plate is moving... Oh, sorry, the plate is moving like this. I got this backwards. No, the plate's moving like this right there. Sorry. And what happens is that these volcanoes are carried off of the hotspot where they die and start eroding because of wind and water, okay? So eventually the active volcanoes in Hawaii right now will be moved off of the hotspot and it will die, right? But that's okay because the hotspot will still be there and new Hawaiian islands will show up over here. Does that make sense? So the Hawaiian Islands we have right now are just the most recent Hawaiian Islands. If you look off the coast of Hawaii back here, there are dead Hawaiian Islands that have eroded down below the surface of the water actually going all the way back up to Russia. Basically, over time, Hawaii leaves this hotspot and erodes below the surface, and a new Hawaii pops up later. So there's been a series of Hawaiis moving slowly across the Pacific Ocean. Okay? Oh, now here's the last question I have about this. If we didn't have plate tectonics, how would the Hawaiian Islands be different? If Earth did not have plate tectonics, how would Hawaii be different? Right. It would basically be just one or two very, very large volcanoes. So one or two very large Hawaiian islands right on top of that hotspot. And ours would probably get bigger than Mars's are because our planet has been active for a longer time. But we do have plate tectonics, so that robs us of being able to hit the record on the size of volcanoes. Okay.